our discussion will focus on the second method in finding the volume of solid of revolution, and that is the washer or ring method. Okay, please take note that the first method, which is the disk method, okay, we consider the region R touching the axis of revolution, and the element is perpendicular to the axis of revolution, so that when it is revolved about the axis of revolution, then a washer is, oh, sorry, it should be a disc, a circular disc is formed. And for a disc, for the disc, no, recall that the volume is equal to pi times the square of the radius times the thickness. So we base the working equation on the volume of the circular disc, okay, which is volume is equal to pi r squared times the thickness. Okay, this time we will have the second method, and the second method is the washer, or sometimes we call this as the ring method. Okay, now, unlike the first method in which the region R touches the axis of a revolution, in the washer method, we consider the region R which does not touch the axis of revolution, just like what is shown here in the figure. We have the region R, and the axis of revolution is the x-axis, okay? So that if we will use the element perpendicular to the axis of revolution, okay, take note that we will use also an element perpendicular to the axis of revolution. When this is revolved about the axis of revolution, a washer is formed. And if we want to get the volume of the washer form, okay, the volume is equal to pi times the outer radius square minus the inner radius square times the thickness. Okay, now, in the case where the axis of revolution is the x-axis and this is the region formed, okay, the plane region R, rather, where it is bounded above by y is equal to f of x and below by y is equal to g of x, so that we will call the curve above as YH, and below we will call this as YL. And if we will focus on the element which is drawn here, which is perpendicular to the axis of revolution, take note that the element does not touch the axis of revolution, so that when it is revolved about the x-axis, then the washer is formed, and the volume, which is based on pi times the quantity r2 square minus r1 square times the thickness of which is the differential of x, and the outer radius is equal to YH, and the inner radius is equal to YL. Okay, the outer radius is the distance of this point from the axis of revolution, which in which the center of the washer lies. And the inner radius is the distance of this point from the axis of revolution, and that is YL. So that the volume of the solid of revolution by integration is equal to the integral of pi times the square of y sub h minus the square of y sub l times the thickness dx. And since YH is equal to f of x and YL is equal to g of x, then the volume is equal to pi times the integral of f of x squared minus g of x squared times dx, and then times pi. Now, in the case where the axis of revolution is the y-axis, okay, let us consider this figure. On the left, we have the region R, and the axis of revolution is the x-axis. The region R does not touch the axis of revolution, and the element is perpendicular to the axis of revolution, and of course, if that does not touch the axis of revolution, so that when it is revolved about the y-axis, again, a washer is formed. Now, this time, the outer radius is determined by the curve on the right, and the curve on the right, which we call as XR, the curve on the left, which we call as XL. XL and XR are both functions of F of Y rather, so that the inner radius is equal to x sub L, and the outer radius is equal to x sub R, so that the volume by integration, okay, based on the volume of the washer, is the integral within the limits of integration C to D of pi times xr square minus xl square times the differential of y, or since both xr and xl are functions of y, then the volume is equal to pi times the integral for within the limits of integration c to d of w of y, this is xr quantity square, minus v of y, okay, this is u XL, okay, and then square it, no, times the differential of y. Okay, so again, we have to remember that if we will use the washer or ring method, the region R must not touch the axis of revolution, and the element must be perpendicular to the axis of revolution, just like in the BS method. Now, to illustrate how to find the volume using the washer method or the ring method, okay, let me share this time the whiteboard. So we will find the volume of the solid generated by revolving about the y-axis rather. Revolving about the y-axis, the area bounded by y is equal to x square. Y is equal to x square is a parabola opening upward, vertex at 0, 0. X is equal to 2. Of course, x is equal to 2 is a vertical line, and y is equal to 0. Y is equal to 0, of course, is the x-axis. Therefore, if we will get the intersection of the curve y is equal to x square with the line x is equal to 2, then we can just do it by substitution. Okay, now when x is equal to 2, of course, y is equal to 2 raised to the second power, which is equal to 4. Therefore, the parabola y is equal to x square with vertex at 0, 0. Okay, that is the intersection also of the parabola with the x-axis at 0, 0. Okay, so intersection is at 2, 4. And if we are going to draw the figure or the sketch, okay, let us consider the x-axis and the y-axis. The intersection of the line x is equal to 2 with the parabola is at 2, 4. And let us assume that this is the point of intersection at 2, 4. And this is the line x is equal to 2. Of course, the parabola y is equal to x squared with vertex at 0, 0 will intersect the x-axis. That is y is equal to 0. The y-axis is, the x-axis rather is y is equal to 0. And the parabola y is equal to x squared opens upward, vertex at the origin. Okay, so hence, this is y is equal to x squared. And we are considering this region R. The region R bounded by y is equal to x squared, x is equal to 2, and y is equal to 0. And the axis of revolution is the y-axis. Okay, hence, we shall indicate, we shall draw a circular arrow here on the y-axis to indicate that it is the axis of revolution. And since the region R does not touch the axis of revolution, only at one point, of course, at 0, 0, okay, then we have to use an element perpendicular to the y-axis. So that must be a horizontal element. So let this be the horizontal element perpendicular to the y-axis. Okay, and this point is determined by x is equal to 2. So coordinates of this point are x, r, y. The distance of this point from the x-axis is y. From the y-axis is xr. And this point on the left, okay, on the parabola, has the coordinates x, l, y. Of course, the thickness is equal to the differential of y. And if we are going to revolve the element about the y-axis, then we will form a ring. Okay, this is of course, if we will just project the element here, okay, and let it be revolved about the y-axis, then we will be able to form or to generate rather a washer. Okay, and this is the washer. Of course, it is circular in form, just like the disc, but there is a hole inside. Okay, that's it. And the outer radius, this is R2. This is the outer radius, R sub 2. And the inner radius is R sub 1. And R sub 1 is XL. R sub 2 is equal to XR. And of course, if we want to get the volume of the solid of revolution of the region bounded by y is equal to x squared as x is equal to 2 and y is equal to 0, we're going to base it on the volume of the washer. The volume of the washer is pi times the quantity, the outer radius square minus the inner radius square times the thickness. And the thickness, of course, is the differential of y since the element is horizontal. So the volume of the washer, which is formed by revolving about the y-axis, the representative element, that is equal to pi times the integral of, okay, r sub 2 is xr. So we will have here xr square minus r sub 1 is xl, so xl square times the thickness, which is the differential of y. And since the variable of integration is y, then we shall consider the closed interval from y is equal to 0 to y is equal to 4. The lowest value of y is 0 and the highest value of y is 4. So we are considering the closed interval from 0 to 4. Okay, therefore the integral must be evaluated from the lower limit 0 to the upper limit 4. And if we will substitute the value of x sub r, of course, x sub r is determined by the line x is equal to 2. Okay, so x sub r is determined by the line x is equal to 2. And x sub l rather is determined by the parabola y is equal to x squared. Therefore, if we will solve for x squared here, we have to get the square root of both sides of the equation so that the square root of y is equal to x. So xl is equal to the square root of y. And the square root of y, of course, is y raised to 1/2 in exponential form. Okay, therefore, um, x sub r is 2. So we will have 2 raised to the second power minus the square root of y. X sub l is square root of y. We raise this to the second power times the differential of y. And this will give us pi integral from 0 to 4 of 2 square is 4 minus the square root of y is y dy. And if we will evaluate the integral, then that gives us pi times the integral of 4 dy is 4y minus the integral of y dy is y squared over 2, and this must be evaluated from 0 to 4. Okay, thus this will give us pi times 4 times the value of y at the upper limit 4. So we will have 4 times 4 minus 4 raised to the second power over 2. Okay, this is the value of the integral at the upper limit 4 minus the value of the integral at the lower limit 0. So that gives us 4 times 0 minus 4 squared is 16. Okay, sorry. 4, rather, we are evaluating y at 0. So we will have 0 raised to the second power over 2, which of course will give us 0. Hence, the volume is equal to pi times the quantity 4 squared is 16 minus 4 times 4, or 4 squared is 16 over 2. That gives us 8. Therefore, volume is equal to 8 pi cubic units. Okay, so we were able to find the volume of the solid, okay, generated by revolving this area, okay, the region R, about the y-axis. And we use the washer method or the ring method, and that gives us volume is equal to 8 pi cubic units. Okay, so remember again that when we use the ring or washer method, the element must be perpendicular to the axis of revolution, and it does not touch the axis of revolution since the region R does not touch the axis of revolution, meaning the axis of revolution is not part of the boundary of the region R. Okay, so this time we're going to consider another example in which the region R is bounded by two curves. Okay, this time we will find the volume of the solid by revolving about the x-axis, the region bounded by the curves y squared is equal to x and y is equal to x cubed. Okay, so of course, y squared is equal to x is a parabola opening to the right, and we have y is equal to x cubed, which is an odd function. Okay, it is symmetric with respect to the origin. So if we will consider the two equations, y squared is equal to x and y is equal to x cubed. Okay, solving these two equations simultaneously, then we can replace x by y squared. Okay, so that y using equation number, okay, we have equation number 1 and equation number 2. If we are going to consider equation number 2, y is equal to x cubed. Okay, since in equation number 1, x is equal to y squared, then by substitution, equation number 2 becomes y is equal to, replace x by y squared, and then raise this to the third power so that y is equal to y raised to the 6. And we can also write this as y raised to 6 minus 1 is equal to 0. And if we will solve for the values of y, so that we can get the intersection of the two curves, we can factor out y, so that the other factor is y raised to 5 minus 1, okay, equated to 0. And equating each factor to 0, we have y is equal to 0, and y raised to 5 minus 1 is equal to 0. Now, if we will use equation number 2, of course, equation number 2 is y is equal to x cubed, no? So let us use the equation y is equal to x cubed. This is equation number 2. And when y is equal to 0, then we have 0 is equal to 0 is equal to x cubed. Therefore, this will give us x equals 0 also. Hence, we have the origin as one of the points of intersection, meaning the parabola and the curve y is equal to x cubed will intersect at the origin. So let us have another point of intersection by considering y to the fifth minus 1 is equal to 0. So y raised to 5 is equal to 1. And getting the fifth root of both sides of the equation will give us y is equal to 1. And when y is equal to 1, then what is x? What is the corresponding value of x? Now, we have y is equal to x cubed, okay? So 1 is equal to x cubed, and getting the cube root of 1, of course, will give us x is equal to 1. And when x is equal to 1, of course, we have another point of intersection at 1, 1. So these are the points of intersection of the two curves at the origin and at 1, 1. And the axis of revolution is the x-axis. Okay, so let us now draw the or sketch the region. Let us consider this as the x-axis and the y-axis. The two curves will intersect the origin, so this is 0, 0. And they will also intersect at 1, 1. Okay, this is 1, 1. Now, if we are going to draw the parabola y squared is equal to x, or x is equal to y squared, okay, it is a parabola opening to the right with vertex at the origin. So this is the representation of y squared is equal to x. Now, if we will graph y is equal to x cubed, of course, y is equal to x cubed. When x is 0, y is 0. When x is 1, y is equal to 1. And it is actually a curve which is symmetric with respect to the origin. And this is the graph of y is equal to x cubed. Actually, symmetric yan with respect to the origin. Okay, and we are considering this region. Now, this curve is y is equal to x cubed. Okay. Now, the axis of revolution is the x-axis. So since the axis of revolution is the x-axis, then we have to use an element which is perpendicular to the x-axis, since we will consider using the washer or ring method. So we can draw the element anywhere on within the region touching the two curves. Okay, this point, of course, will have the coordinates x y upper, and this point will have the coordinates, the lower point on the lower end of the element will have the coordinates x, y sub l. And if we will revolve the region R about the x-axis, then we can form the solid of revolution, and of course, the element will form a washer. Let us have the projection here on the other side. So this is the ring or washer form. And that must give us a whole design. Okay. And of course, this will be the outer radius R2, and the inner radius is this R sub 1. And R sub 1 is actually determined by x, determined by y sub l, which is the distance from the x-axis. So R sub 1 is equal to the lower y, yl, and R sub 2 is determined by the upper y. So R sub 2 is YH. Okay. Of course, Y upper is determined by Y square is equal to X. So if we have Y square is equal to X, if we will solve for Y, then Y is equal to square root of X. Okay. And this will determine Y upper. Now, what about Y lower? Y lower will be determined by the curve y is equal to x cubed. So we call this as YL, we call this as YH. Okay, now since we will use the ring method or the washer method, then it will be based on the volume of the washer. The volume of the washer is pi times R2 square minus R1 square times the thickness. Of course, the thickness of the element is the differential of x. And finding the volume of the element which is revolved about the x-axis, that will give us pi times the integral of, okay, R sub 2 is YH, Y upper square, minus R sub 1 is Y lower square. The thickness is dx. And please take note that the limits of integration will go from x is equal to 0 to x is equal to 1. So we are considering the closed interval from 0 to 1. So lower limit is 0, upper limit is 1. Hence, this will give us pi integral from 0 to 1 times. Y upper is determined by the parabola. Okay, so y upper is square root of x. Okay, we raise this to the second power minus y lower is determined by the curve y is equal to x cubed. Okay, so y lower is x cubed raised to the second power. Okay, and we have to multiply this, of course, by the differential of x, so that the volume is equal to pi integral from 0 to 1. Okay, let us simplify the integrand. The square of the square root of x is x, minus the square of x cubed is x raised to 6, okay, dx. And evaluating the integral gives us pi times integral of x dx is x squared over 2 minus The integral of x to the 6 dx is x to the 7 over 7. Okay, and we have to evaluate this from 0 to 1. Hence, volume is equal to pi times. Okay, the value of the integral at the upper limit 1 will give us 1 square over 2 minus 1 raised to the 7 over 7, okay, minus the value of the integral when x is equal to 0. So that gives us 0 square over 2 minus 0 raised to the 7 over 7, which of course is 0. Okay, hence pi volume is equal to pi times 1 half minus 1 over 7. Okay, so this will give us 7 minus 2 over 14. And 7 minus 2 is 5. Okay, hence giving us the volume is equal to 5 over 14 pi cubic units. Okay, so this is how we evaluate the integral. We determine the volume of solid of revolution using the second method, which is the washer method or the ring method. Now, the volume is determined by considering the volume of the washer. The volume of the washer is pi times the quantity R2 square minus R1 square times the thickness. Okay, and if the element is vertical, then the uh, value of R2 is YH, the value of R1 is YL. Now, if the element is horizontal, then the value of R2 is XR and the value of R1 is XL. Okay, so in our next discussion, we will be considering the third method, which is the cylindrical shell method. Okay, so to recap, okay, in the first two methods, the disk method, okay, we use the disk method if the region R touches the axis of revolution, meaning the axis of revolution forms part of the boundary of the region, and the element is perpendicular to the axis of revolution, thus touching the axis of revolution. While for the ring or washer method, this time the region R does not touch the axis of revolution, okay, meaning the axis of revolution does not form part of the boundary of the region R, but the element must be perpendicular also to the axis of revolution and does not touch the axis of revolution.